So, hello everyone. This is a bonus lecture on the set notation. So in the previous year, I have noticed that a lot of students didn't have all the prerequisites about sets. And so in this lecture, I've just given, or I will just give a comprehensive overview of the most important definitions with regards to sets. So as a motivation, you will later have to deal with so-called sequence. This is what you see over here. You really do not have to understand yet what that means, but just as a motivation, the X will be a set and the Y might either be in that set or maybe it's not in that set. Or to write it more naturally, this Y, sorry, I said set, I meant X. So Y could be in X or Y could not be in X. But in order to know what that means, you must, of course, know what this means, and what a set is. So I will start with the cardinality of a set. But before we talk about sets, let's talk about tuples or about sequences. So sequences are actually tuples. There is no difference, at least not from my perspective. And you see here that there are different kinds of notations. So furthermore, there are 3 different kinds of parentheses. We could either have angular ones or round ones, or you could just ignore them altogether. So then we wouldn't have any parentheses at all. In all these cases, we would still talk about tuples or sequences if you want. Although sequences normally don't use any parentheses. And this is multiplied by whether you have a comma or not. Right, so there are 6 combinations. They are all equivalent, there's no difference. They're just different ways of writing it down. So these are tuples. And the cardinality refers always to the number of elements. So in this case here, if you take X, remember that all these 6 variants are just different annotations or notations, but it's still always the same X. And so the cardinality of X is N, because there are actually N elements, right? There's X1, X2, X3, and so on until Xn. So there are N elements. And this is denoted via these 2 dashes. That's the number of elements, also called cardinality. So these are tuples. One more thing to emphasize is that it's really the length of the tuple. So here, for example, you see that there are 5 elements, so that the cardinality is 5. It's not 4. So you see that the 1 occurs twice, but that doesn't matter, right? There are still 5 elements. So the cardinality is 5. Yeah, in this case here, we see the length is 6. It has 6 elements. So again, the cardinality is 6. It's not 3 because there's ABC. It's 6. Now we can talk about sets. Sets always look in the same way. So some people place a comma, others do not. And but you can pretty much almost always recognize them by these curly parentheses. So whenever you see curly parentheses, then you know it's a set. But just for the sake of completeness, I will also show you another syntax for sets. That will, however, not be used in this course. So the next that I'm going to say is just mentioned for the sake of completeness. You will not see that in our course. So let's assume that N and M here, and there, are natural numbers. You know, the natural numbers are 1, 2, 3, 4, and so on. Then you can use these other brackets here. And with these brackets, this here is actually also a set. And it represents the entire set running from N to M. It's just a different annotation. It's actually not really required because you could still just write down this, right? But still, this also exists in literature. Some people just write it that way. So this is all the numbers in between those bounds. And now this here, the shows that a certain bound is missing. So the round edge now indicates that it's exclusive of this border. So the M number is now missing. It's not included anymore. And you can, of course, do the same thing with the left border, and you can combine it. In this case, they're both not included. Actually, this notation is usually done if the numbers are real. That makes a bit of a difference because real numbers don't have a well-defined predecessor, right? In the natural numbers, the predecessor of 5 is uniquely defined. It's 4. But in the real numbers, there is no unique predecessor because even 4.9999 still has one that is closer, namely add another 9. Right? So here it really makes sense to use this annotation because you can say that you run until 5, but the 5 itself is not included. So in particular for real numbers, this notation makes a lot of sense. But as said, I really just mentioned that for the sake of completeness. We won't use it in the course. Yes. Okay, so for you, the important part is this. Recognize sets by the curled parenthesis. Okay, let's get back to the cardinality. In sets, repetition doesn't count. So you see here that I wrote down this X set and this Y set, but here I claim they are completely identical. And with identical, I really mean there is no difference whatsoever. They are exactly the same set. And this means that whether you write down an element like A once, twice, 3 times, or 100 billion times, it doesn't matter. It's the same thing. It's contained in the set, and that's all that matters. So X and Y are identical. But since X and Y are identical, this also means that the cardinality of X is actually 3. And so what this tells you is that the set cardinality only refers to the number of distinct elements. Yeah, because if you look at this set here, then you see that, okay, we have an A, we have an B, and we have a C. So that's 3 elements. Note that set cardinality isn't recursive. So if you look at this set here, then you see that this has 2 elements. And that is because the outer set does indeed have 2 elements, right? There are 2 things inside. One thing is a D, and the other thing is a set. The other set is ABC. So this set here has a cardinality of 2. Yeah, another example here, again, X is identical to Y. They're just written down in a different way. And so the set cardinality of both are identical, and 4. Okay, now let's talk about the order. In tuples, the order does, of course, matter, right? If you have A and B, then this is not the same thing as BA. They're different tuples. Oh, this as well. Okay. In sets, this is not the case. Sets are completely invariant against ordering. And that means that all these 3 sets that you see, they are, again, completely identical, because the only difference that you might believe to see is that they're written down in a different order. But the set doesn't know about this order, right? It just doesn't matter. It's not really there. So it only knows which elements are inside. And this means that these 3 sets are, again, completely identical. But you also know that repetition doesn't matter, which means that these sets are, again, identical to ABC. And therefore, this is identical to this, and to all the other sets. Okay, so you can put in additional elements as long as they are the same, and you can reshuffle them, and nothing changes the set. Okay, as said above or earlier, for tuples, that's not the case. So if you change the order, you get a different tuple. And yeah, therefore you see that all these sets here below, they're all different. But of course, the cardinality might still be identical. But I think this is clear because the cardinality of a set is just the number of elements. And of course, the left one can have 3 elements, the right one can have 3 elements, but the content is still a different one because the order is different. So now we come to some additional notation. So there is a special syntax. So if you look at this set here, then you see there's nothing inside. So the set is called empty. And because everybody is lazy, right? That's why we create abbreviations and so on. We have special syntax, special symbols for that. And so this here, that's just a 0 or an O. Usually I draw an O and cross it out. And that's the empty set. And for the empty tuple, we use an epsilon. Okay, so this is the empty set and epsilon is the empty tuple. So let's take a look at an example. Here you see that the cardinality of this set is 4 because, again, there are 4 different things inside. We have an A, we have a B, we have some set, and we have an empty set. These are 4 different entities, 4 different things. Also, if we would have A, B, C, and C, then it would also have 4 elements because C is just a letter, but this here, that's clearly not a letter. That is a set that contains a letter. So these are 4 different elements, and therefore the set cardinality is again 4. The cardinality of the empty set is non-surprisingly 0 because, yeah, there's nothing inside, so we have 0 elements. Here, again, a bit more fancy. So the set that contains the empty set has, again, cardinality of 1. That should not be surprising because we saw already here that the empty set is a thing, it's an entity. Right? So this contributes to the set cardinality. It's contained in a set. And again, set cardinality is not recursive. So if we have a set and there's a set inside, and in that set is another set, namely the empty set, then how many elements are in the outer set? Well, 1, a set. Doesn't even matter how that set looks, right? Whether there's the empty set inside or a bigger set or whatever, it doesn't matter. There's 1 element in the bigger set. So cardinality is 1. And this here has 2 elements because the empty set is not the same thing as the empty tuple. Right? They are both empty, but they're structurally different things. One is one is tuple, the other one is a set. Okay, now another annotation that not everybody knows, and that is the so-called power set. And the power set is denoted with 2 to the power of a set. There are also other ways of writing that down, like P of X. That literally means power set of X. But many people also use the 2. And the power set is simply the set of all subsets. Right? So if you look at those inner sets here, A, B, C, and actually nothing at all, like, I mean, the set that contains nothing at all, and also at the other one, then you will see that these are all the sets that exist that you could create using the elements A, B, C. There doesn't exist any other set, right? All the possibilities are covered here. And this is what 2 to the power of X means. So if X is a set, the power set of X, 2 to the power of X, is every single set that you could possibly create using the elements from X. I've called this fun fact. I find this cool. That is that the cardinality of the power set is 2 to the power of the cardinality of the set. Right, so if X has these 3 elements, then what's the cardinality of X? Well, you can just count. It's 1, 2, 3, 4, 5, 6, 7, 8. So we know this is 8. But here I claim that this is actually the same as 2 to the power of the cardinality of x. So 2 to 3, because x has 3 elements, right? There's 3 elements inside. And 2 to the power of 3 is 8. And yeah, I think it's just cool that 2 to the power of a set, this is actually the same as this. I find this cool. Yeah, so there are an exponential number of sets that you can create. You will see that later actually in the logic course, because we are going to create so-called truth tables. And truth tables also talk about all the different combinations of things that you can do. And you will see that truth tables grow exponentially. More notation. Set membership, you have seen that in the very first slide. We write this to indicate that A is contained in the set X. And we can also say A is an element of X, or A is a member of X. It's all the same. And you just cross it out if it's not true. Okay, we again see examples for this. So if our set X contains another set containing A and B, and the letter C, then the set AB is part of X, right? You see that this set here is contained in X, and C is also an X, and actually nothing else is an X, because you see the set X, and you see that there are no other elements. Although you could, of course, argue, hey, wait a minute, didn't you say that A, B, and B and A is also an X? And yes, it is, but that's not a contradiction, because we covered that already, because that is literally AB. There is no difference. They are the same thing. So it's still correct to say that nothing else is in the set. Okay, also A is not in X, right? It's not in there. It's just the 2 elements that you see above. B is also not in there. The set containing A is not in there, and the set containing C is not in there. So nothing else is in there, basically. Exactly, this is in there, and the C is in there, nothing else. Let's make another example. Again, the natural numbers, which start from 1, 2, and it doesn't have an end, which means that the set cardinality of the natural numbers is infinity. And so we know that 0 isn't contained in the natural numbers, and also infinity isn't contained in the natural numbers. So there are infinitely many numbers, but the strange symbol here, this is not part of n, right? Because that's not even a number. That's a strange symbol that we made up, but it's not a number. So infinity is not part of the natural numbers. Yeah, 42 is in the natural numbers, and according to Sheldon Cooper, the best number in the world, 73, is also in the natural numbers. You can Google that in case you want to know why it's the best number. Again, then we have set entailments. Oopsie, sorry for that. No, can you stop? So here we can say y is a subset of x, and we just cross it out if it doesn't hold. And subset, let me give you an example what that means. Well, subset, yeah, let's just go through some examples. So ABC is a subset of ABC, and in fact, any set is a subset of itself. And therefore, this holds again, but that's just because this is exactly the same as ABC. Right? There's no difference. And yeah, so clearly each set is a subset of itself. And yeah, AC is also a subset of ABC. And now let's make a more complicated example. Here, C is also a subset of X, and the set containing A and B is also a subset of X. This here, however, is not a subset, right? You cannot obtain this set from X by eliminating elements from X. But AB, yeah, the set AB is in X, but it's not a subset of X. So actually there is an intuitive explanation on how you can achieve a subset, and that is by eliminating elements from the main set. That's how you obtain a subset. And actually only now when I give this presentation, I've realized that I thought subset would be self-explanatory, but of course there is a formal definition. Let me see whether I can improvise it. So we can write if and only if each element that is in Y should be in X, I think. Yeah. So each little y in the back Y holds Y in X, right? So if every element which is in the big Y also occurs in big X, then X is a superset of Y, and therefore Y is a subset of X. So that would be a formal definition that you could give. Now, another annotation that you will see, in particular in computer science from time to time. I'm not aware whether we have that in this course, but it's still important to know this, is the Cartesian product. And so if you have three sets, X, Y, Z, then you can put this cross in the middle. And what that means is that you can take arbitrary elements from the respective sets and put them together to a tuple. Right, so here this X can be any X from the set big X, the Y can be any Y from the big set Y, and again, the set can be any set from the big set. So this X times Y times Z is really the set of all tuples that you can possibly create by combining all the different elements from those sets X, Y, and Z. So to give you an example, let's say we have a function f, which maps the set consisting of a u times the natural numbers to the natural numbers times g. And the set g is the grades, HD, D, credit, pass, and fail. Then we could that way we could map each student ID to a numerical mark and a textual grade, right? So for example, the function f of u and 1, 2, 3, 5, 6 could be mapped to 87 and d. Of course, you don't need this u comma, right? I just wanted to give you another example for this times operator for this Cartesian object product. And we can also use exponents for abbreviations. So x squared is just the same as x times x. And so you can generalize that to an n. So if you write an n, then here there are n many x's. X star is a bit more complicated. X star stands for any number in the natural. Oh, maybe you didn't have that yet. That might actually come in the next slide. Yeah, you will see that. So that's any number in 0, 1, 2, and so on. So for example, if x is AB times 3 with a star, then x is the set of all tuples, where the first element is from the first set. So we have A, and potentially not a single 3, so just the A, or we take 1 3, or we take 2 3s, and so on until infinity, right? There is no, because the natural numbers don't have an end. So yes, okay, and we can also do the same with the B. So it's 1B, or the B with 1 3, with 2 3s, and so on. And if instead we would not have used the star, but the 2, then we would only have these elements, because we take an element from here, A, and then a single element from the other sets. But again, remember that this, what this 2 means, so it's 3 times 3. So we have A, comma, 3, comma 3. And we do the same with the B, so we have B, comma 3, comma 3. And now finally, we have 3 more operations. So X set union Y. And what set union means is really just putting together both sets. So that's the set of all Z, such that Z is either in X or in Y. So you just take your 2 sets and you put them together. And so here the C, we just swallowed it, because I mean, you could also write it down twice. You just don't do that because repetition doesn't count. So this would be the resulting set. Just put together the sets. Then the set intersection, this computes the intersection of those sets. And so if you look at these 2 sets, then you see that the only thing that they have in common is this is the C, and therefore the set intersection is the set that contains exactly the C, because this is the only element that both sets share. And finally, we have the set subtraction, which removes one from the other. So this reads X without Y. So you take X and remove all the elements from Y. So this is what this says here. It's the set of all elements from X that do not occur in Y. So if you take A, B, C and you subtract C and D, then you start with the set and you remove everything from the set Y. So we remove C, so C goes, we remove D. Okay, we don't have to do anything because it wasn't there. So what's left? The set containing A and B. In conclusion, we are done. The most important point that I would like to stress, if you watched that lecture here, and if you think that, oh, there was a lot of new stuff, then I want you to really focus on this part here, that this lecture covered a lot more that you will need for our course. I don't know, it didn't feel right to just explain 2 or 3 things, if instead I just can cover every single bit about sets. But really the only really important things that you need for this course here is you have to know what this means, namely that an element is part of a set. You need to know what set union means, namely putting together 2 sets. You need to know the intersection, which is the set of all elements that are part of both sets. And you will need the subset relation, which just says that, yeah, one is a smaller part of a bigger set. And I'm not sure about this, but this is just too standard. You really should know that, even if I'm not using this in this course, which is the Cartesian product, which is basically just a combination of all. Let me just give another very quick example. So if we have these 2 sets and there's X, then this Cartesian product here is the set of all tuples where you combine. So we have an A and a 1. We have an A and a 2. We have an A and a 3. And now we are done with the A. We cannot do anything for that anymore. So now we continue with the B. We have the B, and a 1, a B and a 2, and a B and a 3. Right? So the Cartesian product really just means it's a set of all the combinations. And yeah, the 4-on-1 versions of these slides can be found on log. Okay, thank you for listening.